Welcome to Week 5, where you will be learning about what electricity is and how we measure the sustainability of electricity options. In Unit 1, you learned about what energy is, about primary energy trends, and how to define and measure energy sustainability. Going forward, we will divide primary energy use into three main categories: electricity, transportation, and heating. Unit 2 will focus on how to make the electricity sector more sustainable, and Unit 3 will focus on how to make the transportation and heating sectors more sustainable. This graph shows how the three sectors stack up in terms of amount of energy used and the primary energy sources that supply each sector. Electricity makes up the largest proportion of total energy use in the U.S., and it is supplied primarily by coal, nuclear, and natural gas. Heating, including industrial, residential, and commercial heating, makes up the second largest proportion of total energy use, and it is supplied mainly by natural gas and oil. Transportation makes up the remaining proportion and is mainly supplied by oil. This week you will be exploring the answers to these questions related to the electricity sector. What is electricity and how does it work? How do electricity profiles differ from region to region? What is the electricity grid and how does it work? What are some advantages and disadvantages to the U.S. electricity grid? Which sustainability indicators should we use to evaluate the sustainability of electricity options? And how does electricity interact with the other main energy uses, transportation and heating? To answer the first question, explore the video Energy 101, Electricity Generation, and readings 2 through 6. These resources provide a basic overview of what electricity is and how it works. However, there is some information these resources do not provide that will be important to your understanding of sustainable electricity options going forward in this course. First is the distinction between central and distributed generation. You should be aware that when people talk about electricity, they are usually referring to the dominant paradigm of centralized electricity generation that is the basis for the U.S. electricity grid. In this paradigm, large power plants of the megawatt or gigawatt scale, which are located far away from where the electricity is being used, supply electricity across high voltage transmission lines. An example would be a 500 megawatt coal power plant or a 1 gigawatt nuclear power plant that supplies electricity for an entire region. The high voltage transmission lines that carry electricity from the power plant to the distribution network have environmental and health effects, including disturbance of habitat and safety issues, among others. Reliability of centrally generated electricity supply depends on the entities that are generating and supplying the electricity. Consumers do not have to have any understanding of the system in order to use it. Prices fluctuate based on market forces in many cases, but are pretty stable in the near term. And changes to the system usually come through top-down policies in which the government mandates that utilities do something differently. There is an alternative to this paradigm, and that is distributed generation, which includes small generators of the kilowatt size or maybe as large as 1 megawatt. These generators are located close to the point of use and don't usually require transmission wires, eliminating health and environmental effects associated with that part of the system. An example would be a small wind turbine providing electricity to a farm, photovoltaic solar panels providing electricity to a house, or even a 1 megawatt diesel generator providing electricity to an island community. Even small fossil fuel generators can improve the health and environmental effects associated with electricity generation because they eliminate the need for transmission wires. Typically, the person who is using the energy must make the investment in distributed generation options, and this can involve a long payback period to capture the benefits of a large upfront investment. The price of energy then depends on the cost of the investment and the terms of the loan used to pay for the investment. It also depends on what policies are in place to encourage investment, such as net metering policies, which encourage people to install wind and solar options. Since the consumer usually has to make the investment, the consumer must be educated about electricity in general and the options he or she can choose from. For this reason as well, many of the policies that encourage distributed generation come from citizen involvement or bottom-up grassroots policies. We will discuss many of these ideas and issues more in depth as we examine different energy options, But for now, be aware of the fact that central and distributed generation are two different electricity paradigms and have a basic understanding of the differences between them. As with many energy concepts, definitions for central and distributed generation vary and can often be vague and misleading. For the purposes of this course, we will define central generation as the production of energy at a large 500 to 3,000 megawatt power plant and transmitted through an infrastructure to a widely distributed group of users. And we will use the abbreviation CG to represent this option. We will define distributed generation as an electric power generation source that is connected directly to the distribution network or on the customer side of the meter. This definition does not include a specification of the size of the generation, but does specify that DG doesn't use transmission wires because it is connected directly to the distribution network. To visualize this a little better, the four main components of a centralized electricity system include generation, transmission, distribution, and use. Generation includes the power plants that convert coal, natural gas, uranium, etc. from primary energy to electricity, which is secondary energy. Transmission includes large high-voltage wires that carry electricity from the power plant to the distribution network. The distribution network includes smaller, lower voltage lines that carry electricity to the end users. And the use includes the three main end users: residential, commercial, and industrial. Distributed generation cuts out the transmission step and either goes directly from generation to distribution or directly from generation to use, depending on how big the generator is and which end user type is receiving the electricity. For example, an industrial consumer would require a larger distributed generator with a small distribution network, while a residential consumer would have the generator at the point of use with no need for distribution wires. Here is a reminder of the difference between the three main electricity end-use sectors. In Unit 1, we identified four main primary energy end users, with transportation as the fourth end-use sector. But since the transportation sector does not use much electricity, at least currently, this may change if electric vehicles are adopted more widely, we exclude transportation from the electricity end-use sector list. Another concept that you won't find in the readings but is important to understand relates to the question, what is the electricity grid and how does it work? The readings and interactive website should help you answer these questions. But one thing they don't explicitly discuss is the difference between direct and alternating current. Direct current, or DC, is electricity that flows in one direction. It is direct. Alternating current flows in one direction first and then the opposite direction. When graphed, it follows a sine wave pattern, as opposed to direct current, which would be a straight line. There is more we could say about this, but we don't need to get bogged down in the details. What's important for you to know at this point is that our entire electricity grid is based on alternating current, or AC power. The reason we have an AC grid comes early in the development of the electricity grid, when AC was selected because at the time it was safer and more efficient. Now, however, DC is just as safe and now more efficient, but we are stuck with the AC grid we have. This is important for at least two main reasons. One, you will be learning about the three main sections of the U.S. grid: East, West, and Texas. These sections are seen as completely different parts of the overall grid because they run on different frequencies. Although they all run on alternating current, their sine waves don't line up with each other. So if a generator in Texas wants to send electricity to Arizona, for example, that electricity has to go through a special and very expensive transformation process to be converted from Texas alternating current to Western alternating current. The second important point is that some renewables like solar and wind produce direct current electricity. So if we want that electricity to be used by a household or business that is wired for the alternating current grid, we must use inverters to convert the electricity from direct current to alternating current. And this reduces the efficiency of the energy option and raises its cost. Another thing the readings and videos don't explain much about is the fact that not all states regulate electricity in the same way. States have a lot of control over how electricity is generated, distributed, and priced within the state. Historically, all states regulated electricity completely through vertically integrated utilities, in which the utility owned and controlled the generators, transmission and distribution networks, and sales to end users, and the State Public Utility Commission set the price of electricity for the whole state. A little more than half of the states are still regulated in this way. See the white states on the map. The rest of the states have gone through various stages of restructuring since the 1990s. Basically, this means that either the generation or the sale of electricity has been deregulated, and many companies are allowed to compete in a semi-free market. One goal of this restructuring was to lower electricity prices, but this goal was not quite achieved, so some states are shown as suspended or yellow in color on this map, because they originally allowed a lot of competition in the electricity market, but have scaled that back and added more regulations since the restructuring began. When studying sustainable solutions to electricity issues, it is important to know that state regulation policies exist because this can affect price and other aspects of electricity. To view the specific regulation structure of each state, go to the website listed at the top of the page and click on the state of interest. The states that still have regulated electricity markets, the white ones on the map, include buyers from the residential, commercial, and industrial sectors who pay a set price of electricity to a utility. The utility is vertically integrated, meaning that generation, G, transmission, T, distribution, D, and sales, S, are all controlled by the utility. The costs of generating the electricity are covered through electricity charges, which are set by the Public Utilities Commission, the PUC, through rate of return pricing, meaning the utility is guaranteed a certain rate of return on their investments, usually 10%. The yellow and green states from the map have restructured electricity markets, which may mean any or all of the following. Buyers and sellers are allowed to enter into bilateral agreements, agreements between two parties, in which they agree on a certain price of electricity over a specified time period. The buyers in these cases would be industrial and large commercial customers, or retail companies that are selling electricity to residential or small commercial customers. Most restructured states have competition in the retail sales of electricity. The website shown here explains how retail competition works in the state of Maine, which is a restructured state. In some states, there is also competition in ancillary services, such as reactive power and reserves, which are services that aren't as obvious as generation, transmission, and distribution, but nonetheless important to the reliable operation of the grid. If there is competition in the generation of electricity in a restructured electricity market, then the price of electricity is set in a day-ahead market based on locational marginal pricing. In this pricing system, the price of electricity is set by the most expensive generator that is allowed to operate in the market, and generators are selected to operate on the lowest cost of operation. For example, let's imagine a set of loads. These would be appliances, lighting, heating systems, etc., that are turned on and demanding electricity. Let's imagine these loads require 600 megawatt hours of electricity. And there are 3 generators in the market who are available to supply electricity. Generator A has a capacity of 500 megawatts, meaning it can supply 500 megawatts of power, or 500 megawatt hours of electricity over the course of 1 hour. Generators B and C have capacities of 100 megawatts each. The combined capacity of all generators is 700 megawatts, 100 plus 100 plus 500. But only 600 megawatt hours are demanded. Which generators will operate in this example? Well, the answer depends on how much it costs for each generator to operate. Let's say it costs generator A $60 per megawatt hour of electricity it generates, $80 per megawatt hour for generator B, and $100 per megawatt hour for generator C. The market will select the lowest cost generators first, so generator A will operate first because it is cheapest, and then generator B will operate to make up the extra electricity demanded. Generator C will not operate because it is the most expensive and it is not needed to meet the demand. The price of electricity is set by the highest cost generator that is operating. So in this example, the price that all buyers in the market must pay is $80 per megawatt hour. This allows generator B to just cover its cost, and generator A gets a profit of $20 per megawatt hour, the difference between the price set on the market and generator A's cost of production. If demand increases to 650 megawatt hours, for example, generator C will come online and supply the extra 50 megawatt hours that is needed. In this case, the price of electricity is now increased to $100 per megawatt hour, and generators A and B make a nice profit of $20 per megawatt hour and $40 per megawatt hour, respectively. This graph shows the marginal cost in dollars per megawatt hour of specific generators in the United States. As you can see, hydro units have the lowest cost because the costs to install them have been paid off for decades and there is no fuel cost. Current nuclear plants have low costs too because they have mostly been paid for as well. Fossil fuel plants have variable costs because they depend on the price of fuel at that time. In 2007, natural gas and oil-fired power plants were the most expensive to operate. If the demand for electricity intersects the supply available at the line shown here, then the electricity would be supplied by hydro, nuclear, coal, natural gas combined cycle units, and some of the cheaper oil and natural gas combustion turbines. And the price of this electricity would be set at around $80 per megawatt hour. These trends change with time. A year later, the cost to operate coal power plants increased, and so did the cost to operate the oil and natural gas turbines. So a snapshot at this point in time with the same demand would show the price of electricity increased to around $90 per megawatt hour. And these prices change faster than on a yearly basis. They actually change by the minute, and the markets in charge of these transactions operate much like the stock market, buying and selling electricity every moment of the day. So who is in charge of this complicated system? There are a lot of different entities that operate together to regulate the U.S. electricity system. NERC, the North American Electric Reliability Corporation, FERC, Federal Energy Regulatory Commission, RTOs, Regional Transmission Organizations, ISOs, Independent System Operators, and PUCs, Public Utility Commissions. Here is some information on NERC's responsibilities. And this map shows the major interconnections regulated by 10 regional NERC reliability councils. Here is some information on FERC's responsibilities. FERC is in charge anytime electricity and other energy crosses state lines. Anything that stays within the state is regulated by the state itself. RTOs and ISOs set electricity prices and rules for specific regions of the North American electric grid. These are the organizations that control the regional electricity market, which sets the price of electricity through locational marginal pricing for restructured states. So, for example, ISO New England oversees the market that sets the price of electricity for all of New England. The state-run PUCs regulate the rates and services of a public utility in states that are still regulated, and in some of the restructured states, like Maine, where the PUC sets the standard offer price of electricity that certain retailers like Bangor Hydro, now Emera, use. But other entities like Electricity Maine are allowed to sell electricity at a different price if they want, so there is retail competition. All of this information presented here is not included in the readings and videos and should help you answer questions 1, 3, 4, and 6 on this list. The readings and videos will provide more information on these questions as well as information on questions 2 and 5. For question 2, you will need to explore the interactive electricity grid map and return to the interactive maps from week 4, with an eye on electricity this time and not just primary energy. The answers to question 5 will come after you have reviewed all of the materials and have come to a better understanding of the electricity system. You will need to review concepts from Unit 1, such as what is a sustainability indicator, what are the 4 main categories of sustainability, and what is the balanced approach to measuring sustainability. And make sure you select measurable indicators that represent the major issues in electricity. I hope you enjoy learning about this exciting and dynamic topic of electricity this week.